How you guys doing? All right. Long weekend was good? All right. So you're stoked to be back to learning now? Something like that. Oh, okay. So, all right. There we go. Kevin, right? Appreciate the enthusiasm, Kevin. All right. So we're going to move on from the sun today, and we're going to start to look for a way to put stars into families in such a way that we can start to tell a coherent story about them, right? So in some sense, there's a little bit, do you guys know what taxonomy is in biology? Have you ever heard that before? You kind of group animals together. You know, originally they tried to do this by the way that animals looked. And to some extent, a lot of the family trees were set up that way. And then when they discovered genetics, they had to kind of go back and revise all of those stories. And so that's kind of what we're doing at this point with stars. We're going to start clustering based on their appearances and different features about the way that they exist with respect to other stars. And we'll try to use that to tell an evolutionary story about the whole neighborhood, the galaxy eventually. And there's serious troubles with pulling that off, but I want you guys to understand the ways that we've attempted to do it in the past and the way that it's being updated. So just like in biology, we discovered ways to look at genes, all of a sudden we have to rethink that. The same thing is happening here as we begin to learn new things about the stars that we never imagined before. So in order to tell that story, we have to take a really close look at how light itself works. And I know we've talked about light as a conversation. And we've talked a little bit about how the stars generate light, at least two different hypotheses for how they generate light. One of them being part of the standard core fusion model that your textbook has championed, and we went over it in class last time. The other one being from the liquid body of the lattice of the hydrogen itself. So I would be curious to hear from you guys something that you remember that's interesting or confusing from last class so I can give you guys some attendance points. So I'm not going to call people today. You can just raise your hand, and then whoever's not checked by the time we get to it next week, I'll sweep you up next time. Yes, in front. Please tell me your name again, though.
Sandra.
That's right. I'll get there, I promise.
That supernovas and sort of other stars squish stuff together to make metals and other heavy metals, and how our sun makes like hydrogen, and specifically like Chernobylsky's star.
Chernobylsky's star.
Like that. Like how they found all this metal around it, and they're like, oh, it must be aliens or something, because they don't believe, or at least they couldn't really find how it can create the super heavy metal that they have.
It's very short-lived heavy metal is the weird thing. So, you know, things like uranium decay, right? And you can make nuclear power out of them. Let's be optimistic. You can also make bombs too, but these things, these atoms that fall apart, they do the opposite of fusion. We call it fission. There's a lot of elements that you can make in a laboratory that won't live very long. They're not stable. Those atoms just kind of tend to bust apart. And some of those are the elements that they've seen in the spectrum of that star. So yeah, it's pretty bizarre. So yeah, aliens or another road to fusion? That's the real question there. Over here on the side, yeah. Remind me your name?
Aiden.
Aiden, all right.
I had the same question practically, but I wanted to do extra research, but never got the time. Is there a star that doesn't follow the rules that we've found?
Which rules?
Like fusion, the power itself, anything like that?
Not really. Well, the real question becomes, so like Chernobylsky is an interesting example because the model for fusion that is the popular model for the last 100 years since Eddington has all of the fusion happening in the core, right? So, and then it takes, you know, eons for the light, like millions of years for the light to bounce around inside the star somehow and then come out the other side. Presumably the convection of the atoms inside also takes a really long time. And so the interesting piece about Chernobylsky's star being an exception to that is that somehow these really short-lived, there's also, you know, well, I'm not going to speak out of turn because I don't know the actual numbers. There's some really short-lived elements too they've seen in Chernobylsky's star as well, but the longest of which live only like a year or something like that. It's also not a big enough star to have fused that heavy of an element because remember, garden variety stars like our sun can only fuse hydrogen. It's the littlest atom there is. It's really simple. It's only got one electron, one proton. It's very simple. So squishing it together is among the easier fusion reactions. In order to get metals, even in order, I wish we could look at this periodic table. These are all the heavy stuff down here, but even to get some of the slightly larger than hydrogen atoms, you need new processes to happen, and we'll talk about those later. But they're in bigger stars for the most part, is what it comes down to. Chabelsky star is a pretty small star, so it's unclear how that's possible. So, when it comes to fusion, it's a really energy-intense process. It's hard to imagine any place other than a star where that could happen at. There have been people who have talked about kind of processes at the center of galaxies as well, but there's probably stars there too, so it's not necessarily separate. But yeah, if you wanted to, I'm not going to really outline this for you guys right now, but there will be a research project instead of a final exam in this class. And I'm still toying with the exact outline of that, but I think it will be following up on something really crazy that you've heard in this class, essentially, and trying to find alternative perspectives on it and argue with yourself about it and present that. So little half-baked right now. But I want you guys to have the opportunity to go down a deeper rabbit hole with some of this stuff. So yeah, if you follow up on it, I'd love to hear more next time, or whenever you get a chance to. You could also do it as part of your research project. What other thoughts do you guys have? Yeah.
One thing I brought up pretty early in the class was Earth being the densest thing in our solar system, and I thought that was really interesting. But
it is pretty weird, huh? Pretty strange, and honestly, it only gets stranger if you'd been around with us last semester when we talked about, the different models we have for how these planets form, because that's actually a really fun story that's on the move. It's kind of beyond the scope of this conversation, but how in the world do you squeeze all this really dense metallic stuff together, right? Our planet is largely metallic. There's a lot of silicon, right? Silicon dioxide rock, let's call it. But there's also a lot of iron and nickel down below our feet that's really dense. And so how in the world do you pull that off? And there turns out to be a really difficult problem. You would say, well, gravity is nice. It pulls things together. And it's true. It does. But turns out gravity is really good at pulling little dust particles together over time, as long as they're in a fluid pattern where they're staying basically in the same motion over time. But once you get little pebbles, it's really, really hard to get pebbles to stick together, because what happens when pebbles bump into each other? They pop away, right? So there's this intractable problem in this accretion model for these rocky planets where it's virtually impossible to turn a pebble into a boulder with gravity. So there's we unfortunately don't have time to unpack the different ideas about that, but they're quite interesting. Yeah.
I thought that it was interesting that there was a theory about how the sun was just made of gas, because they thought that you could hydrogen as much as you want, it would stay that way.
I'm sorry, one more time. I was writing your name now.
They thought that the sun was just made of gas because they thought that you could compress hydrogen as much
Oh, yeah.
as you could, and that it would stay.
Yeah, I mean, well, that idea, that experiment was done more than 100 years ago, almost 150, 125, something like that. That's if you think about how far, how advanced our laboratories must be compared to these laboratories that you see from the 1800s. Yeah, we've come a long way, and those phase diagrams have changed a lot. To the point that actually astronomers, planetary scientists, have no problem with the idea that the interior of something like Jupiter must be liquid metallic hydrogen because of the pressures. So that's an interesting piece of the puzzle there. I think the biggest problem is that the model for powering these stars depends on these ideal gas laws and so forth. And most of the above-board fusion approaches on Earth that you'll read about in papers and stuff are using that gas approach. You in the back, yeah. Tell me your name, guys, by the way. Help me out.
Alex,
Gotcha.
I thought it was interesting how we were talking about particles. I think it's interesting how language can change how what something means. And so to a average day non-scientist person, a particle would just move something, but an electron particle is something completely different. And so I think it's interesting how language changes throughout the subject.
Yeah, it's funny too, because sometimes you talk with scientists, you talk with peers as scientists, and people will be like, oh, you're just being semantic about this. And it's funny because when you think about it, language is really all we have. Like, yeah, we can make some math equations to describe our experiments, but we still need to explain what the equations are saying about reality. And so language is not some trivial thing, right? It's really the way that we get what's in our head into somebody else's head. And so I think that, moreover, more so than in fiction or poetry, where words can mean lots of different things. I don't know. I think one of the reasons that lyrical music appeals to people so much is because it can kind of mean anything, right? You can kind of insert yourself into the song a little bit, If you're having like some particular experience in life, you like have a song that comes on, and it's like, oh well, like I can insert myself here because the words are so multivalent. They have so much. They're so accessible and they can mean different things. But in science, of all places, we have to be really careful that our words mean exactly what we want them to mean. And yeah, it's really surprising to me that word particle snows a lot of people. But even physicists who use the word on a regular basis still tend to treat it as a little blob of something when that's convenient, but then like some wave structure when that's convenient. And just, the math works, so don't worry about it. But it could confuse us really badly. That's a good point. What else? Yeah. Isabella, is it? Yeah.
I don't know if we touched on this in class specifically, but I thought it was really interesting that like stars are different colors.
Yeah, we'll talk about that more in just a second. We'll get into that. Yes. Summer. Yes.
We talk about brown dwarfs having an upper and lower limit with atoms. Like if they gained or lost one, they would become a sun, or they would ostensibly potentially become a planet.
Yeah.
That means that stars might have other lives as planets.
Yeah.
And then you
Just a thought experiment.
mystically talked about that, so we get into it later.
I think, yeah, we'll get into that later because there's a really cool study about disappearing stars. Well, we're going to talk about the death of stars. I don't know a better word than these like biological words like lives and deaths, right? I don't think that anybody is trying to promote that stars are conscious entities, although that's an interesting idea that we could play with. But yeah, when we talk about the timeline for a star, its evolution across time, the one that your textbook really champions is these explosive processes, which are nice because they give us a means to generate the energy necessary for the production of those big heavy metals and so forth. But the problem is we don't see a lot of those. We actually haven't seen a supernova in our galaxy since the time of Galileo, which is crazy. So you think, perhaps that's just huge geological timescales that we're not familiar with. But there's another piece to that puzzle. I'll get into it when we get there because I want to make sure that we unpack all the details of it.
Did we know it was a supernova? Wasn't he the first person to point a little telescope at the sky? What if it was just a...
Well, so these supernovas, when they do happen, it was a star that was so bright you could see it in the daytime. So something special happens, yeah. And the supernovas do leave remnants, right? There's traces of what happens in their aftermath, and some of that's still visible for Galileo's supernova. But yeah, there's not a lot of them. But we're getting ahead of ourselves a little bit because what we're going to try to do is, by constructing some families of stars, we're going to try to place them on a timeline of how they evolve over time. And so stars look different at different places in that timeline, in their lifetime, if you will. And hopefully we can start to build a story of how they live and die. Yeah.
So with that, with Burnett, is it
It's
able?
Jasmine, right?
With Burnett, is it able to help with that timeline?
With what? I'm sorry.
Remnant of like supernova.
Mm.
Does that help with the timeline, or does it not? I mean, I know it's the death of stuff, but like, are we able to observe it and get some maybe some points?
Yeah, so we can, right? So we do use it to construct a piece of that story, which, and we'll talk about some different interpretations of that, what's left over afterwards. There's a sort of nebula that we see left over. So we're getting way ahead of ourselves though, because we need to see what are the different appearances of stars. What does it say about where they're at in that timeline before we can start talking about theories for how they're born and how they die. I honestly can't think of a better language than born and die. I know those are completely inappropriate, but I just can't beat them. If anybody has ideas, I'd love to hear them, honestly. Yeah, so stars start and they stop at some point. They stop being stars. The idea with the brown dwarfs is kind of a thought experiment, right? I've never heard anybody else really promote that way before, but it seems to me to be a logical necessity that the difference between a brown dwarf and a star is not compositional. It's not what it's made out of. They're both made out of the same thing. It's just that one has more atoms in one place than the other. That's it. And so the line is really thin at some points. And it's at least seems logical to me that there must be instances where it spends time on either side of that break point where it starts fusing neutral hydrogen all of a sudden. Because actually brown dwarfs do some fusion. It's just a heavy hydrogen kind of fusion. So they're not glowing quite as bright, but they do a little bit. They're still really heavy. They're kind of like Jupiters with more hydrogen crammed into them. They're not necessarily even, like in terms of their radius, they're not necessarily bigger than Jupiters even. They're just heavier. They got a lot more stuff packed in. So, other thoughts, folks? In the back, yeah.
I think it's cool that they really like hold down some of these kind of like burn out.
Yeah, I think that I'm glad you guys are keying into that. I mean, the evolution of brown dwarfs, the evolution of planets, all of these things are cooling off. There isn't much of a place in the story that we're going to be building, especially with respect to your textbook and with respect to the standard model that's been promoted over the last 100 years. There isn't really space for stars just cooling off, which has really always struck me as quite bizarre, right? So that's what I keep coming back to, and don't worry, we'll have ample time to talk about these supernovas and so forth. But that's generally how we're taught that stars end their proverbial lives, is through these really violent catastrophes. But it seems to me that, following from this thought experiment with the brown dwarfs, that some portion of them must simply just putter out as well. Maybe it's an enormous proportion of them. And there's some evidence to suggest that's the case, but I want to crack that open for you when I have the numbers in front of me when we get there. So yeah, hang on to that idea. It is tantalizing and interesting though. But perhaps less exciting than explosions that result in all sorts of incredible, beautiful apparitions in the sky and black holes and things like that. What else? Yeah.
I want to know that how the difference between the stars and galaxies using their spectrums.
Well, between stars and galaxies, yeah, that's an interesting point. I think we'll talk about that a bit when we get to galaxy formation. They actually, for what it's worth, when the first not even the first astronomers, sorry, when astronomers 100 years ago, earlier than 100 years ago, let's say the end of the 19th century, they looked up at the sky, they were trying to tell a story of how solar systems formed. So they actually saw galaxies, but they didn't know they were galaxies. They thought that they were solar systems forming. So they saw the swirling shape of galaxies. Has anybody ever seen a galaxy through a telescope before? Yeah? You can see them. You can see, if you have a very nice clear sky and a good telescope, especially if you can do some photography and time lapse it, they are observable just with the naked eye. So people saw this swirling and they thought that that was the creation. And it wasn't until they got much higher powered, really big telescopes, huge ones like the size of this room, that they were able to actually resolve individual stars inside of those, they called them spiral nebulae at the time. And so then they had to kind of pivot. And it was this really crazy moment. It was in the 1920s, actually, when people said, oh my goodness, I think that there's lots, not only is the Milky Way not the whole universe, but I think there's lots of Milky Way. There's a lot of galaxies out there. And so the size of the universe, expanded by thousands and millions of times when they realized that, because all of a sudden these little tiny swirling nebula that they thought were baby solar systems became galaxies full of trillions of stars each. So a lot of that was just resolution, but we'll talk about, and each one of those galaxies can tell us, hopefully we can learn about the age of the galaxies and their own evolution by what families of stars exist inside of them at any given time. So we'll get there, don't worry. We'll work our way towards galaxies eventually. What else? Levin.
Do you know what elements are made in the biggest stars?
Well, presumably the biggest stars are making the biggest elements, and they have the most violent ends to them. We haven't actually observed all the elements in the cosmos, which is kind of interesting, right? So there's certain elements on here on this periodic table that were predicted, that were eventually found or synthesized briefly in laboratories, just because they fell into a pattern with respect to where they should be. But yeah, there's, what's really interesting is that, like, our sun has huge elements in it, actually. And the theory is that they're not made there, that they were leftovers from a previous sun that lived and died. So the story that we're going to work towards is that the bigger a star is, the more pressure that it exerts on itself gravitationally, therefore the shorter it lives. So the idea is that when these galaxies are born, they kind of, all these big heavy stars burn out really, really quickly, and they leave behind a bunch of heavy metals that contribute to the formation of planets and end up in other stars and stuff like that. So we'll get there. But yeah, it takes a huge star to do some of these huge elements, which is why when we see something like a short-lived element in a little star, we have to really ask some hard questions about how the fusion process is actually happening, or, like, are aliens dumping their trash in it? Maybe. Yeah. It's weird, though. What else? Anybody? Yeah. Yes, sir.
If we have all this evidence to suggest that the sun isn't just gas and instead is using some sort of lattice structure, why do we still use that model? And especially since we're developing all these fusion reactors that aren't really able to do fusion, why do we still use that model?
That's the million-dollar question. And I think there's two ways to approach the answer to that. One's like a little more tinfoil hat, and one is a little more sociological. I think they're both kind of interesting. So, one possibility is that, let's just go with the tinfoil hat one first, because it's kind of exciting. So one possibility is, you guys know about the Manhattan Project, right? So World War II was a big nightmare, and there was a real rush to develop a bomb that would end the war, essentially. So did anybody see Oppenheimer, the movie? Yeah, pretty. What'd you think? Is that right? Yeah. Kind of tells the story of how the state, the US government, scooped up all the smartest nuclear scientists, all the quantum physicists, and secretly ushered them away to this place in the desert to work together on this project. Now, a huge part of the success, well, at least the way the story goes, is that a huge part of the success of that project was that it was done very secretively, and there was a lot of, let's say, smoke screen to hide the fact that they were working on it. Oh, we're never going to figure out how to do this nuclear bomb thing. We're nowhere close to figuring it out, right? And then all of a sudden, we have one, right? And it's good to go. So in my mind, I do find it a little hard to believe that nobody realizes that there's a better approach, perhaps, to fusion, or let's say a better way to understand the stars. It might be profitable for a state to not publicize that they're on the verge of having something like that, and to sort of have some above-ground smokescreen that they're just tinkering away on this ancient process that nobody really sees any serious progress with. But as long as that's where all the public attention is, perhaps that's profitable. And then one day, that state, hopefully our state, and not some oppressive competitor, will come out with that technology when it's necessary. So it might be already functionalized and They're just not talking about it. So that's one possibility. The other possibility is that there's this very interesting and incremental way in which science is done that we've been talking about, which is kind of like, say any of you guys want to become scientists. Well, what you'll do is you'll get your undergraduate degree, and you'll apply to a graduate program, and you'll find a mentor, and your mentor has probably been slaving away in his lab for the last 50 years, studying some part. Let's say you go into astronomy. He's been studying some particular aspect of how stars work or something for the last 50 years, and he's going to essentially give you a project that adds a little piece to that story, and you're going to do that. And in all likelihood, that's a well-funded project, and you'll probably, if you go and become a professor and start a lab, you'll work on some little piece of that. And so you kind of get this game of telephone over the years where people are all sort of adding little bits of tinsel to the Christmas tree over multiple generations, and you kind of build up this story that everybody's comfortable with. A number of philosophers of science have written about this, where people will basically tell stories about science until long beyond their expiration date, because they're very comfortable with the narrative that they've been building. And of course, in the advent of scientific careers, it becomes very stable and safe to study something that is part of the general paradigm that everybody's comfortable with. And then one day, it breaks. It becomes, the evidence builds up to the point where it just doesn't make any sense anymore. Sometimes that can take multiple generations. The most famous one the textbook last semester harps on is the Copernican system versus the Ptolemaic system for basically the Earth being at the center of the solar system versus the sun. And, Copernicus put together his model, the one that we essentially have today of the solar system. He put that together very early in his life. He famously carried around a little notebook in his breast pocket, and he would discuss it with people throughout his life. But he didn't really want to ruffle the feathers of people, and he didn't see it as being a particularly productive avenue to start shouting from a tower that everybody was wrong about it. Because, well, the people who are the professional scientists in his day didn't want to be told they were wrong. The church had a lot of influence in that day as well. But what's really fascinating is that, he died. He published his writing basically on his deathbed because the printing press had just come out, so he self-published it. And people started circulating his work and started thinking about it. And Galileo famously came along in the next generation and actually took that idea and made a big scene out of it and got in a ton of trouble. He actually got put under house arrest until the end of his life. His books were not allowed to be published and all sorts of terrible stuff. And eventually, people just found the argument really compelling, and they were just staring in the face of information that just didn't make sense, especially because the telescope was born at some point around then. People started seeing, one of Galileo's really convincing observations was he looked out and saw that Jupiter had individual moons going around it. And he was like, that's really interesting. Like, couldn't that be what's happening here with the sun as well? He also saw that Venus had moon-like phases on it, as if it was orbiting a sun or something like that. So all these new pieces of information come to light. People struggle with it, sometimes for 100 years, 2 generations before let's say the consensus, the overwhelming majority of the experts in the field just can't stand the old story anymore. And we usually call that a scientific revolution when it happens. And honestly, they're quite predictable. We have scientific revolutions in different domains every 50, 100 years. So, it's a weird situation. I don't know. We'll see. Yeah. Oh, goodness. That's interesting. See if we can get it back online. The other part of that story is that using the ideal gas laws and using the different pillars that we talked about with the gaseous sun, the broad pressure broadening of lines, the nebular collapse solar system model that we've been living with for 300 years, a lot of these pieces fit really nicely with the gaseous sun, and people aren't very anxious to abandon them. And there's actually another piece of this puzzle, I think, that makes the paradigm shift even more difficult to pull off, which is this thing that we call the cosmic microwave background radiation. We're going to spend a good amount of time on that, But the cosmic microwave background radiation is also a perfect black body, and it is supposed to be the remnants of more gaseous plasma from the beginning of the universe. And so, again, if you talk to an astronomer and you say, well, that's kind of weird that the sun has this perfect black body curve, I didn't think gases could do that, they might reply, well, we know that the cosmic microwave background radiation did that, and it was made out of a gas as well. And so there's a lot of circularity in this reasoning, right? And we'll talk about different ways to explain the CMB that perhaps aren't as cosmic. So, yeah, revolutions are hard to come by. There's much to be gained. It's also unclear what actors are profiting from keeping things under wraps too. So we'll see what happens. I'm very hopeful I'm going to get to talk to a lattice confined fusion scientist soon. I've been going back and forth with the NASA bureaucrats this week, and I think they're going to let us through the hoops to be able to talk to somebody very soon. It seems like it. We'll see. So hopefully I can report back about that. Any more thoughts or concerns? Fusion? Yes, please.
This might be like kind of an unanswerable question, but what's like the biggest thing that would have to be reconsidered if the new model about how the sun works was accepted?
Tell me your name really quickly before I answer that.
Arthur, but I'm in the system as Renee.
Gotcha. Let me make sure I mark you down. Arthur. What's your last name? Okay, gotcha. I mean, this is perhaps the other answer to Kai's question too. Unfortunately, almost everything, which is horrible actually. If we actually accept that you can't generate a black body spectrum from something that's not a liquid or a solid, which, like I say, every laboratory experiment on Earth that we've ever done would point to that being the case. The only examples of black bodies that aren't from liquids or solids turn out to be the sun, or the stars, let's say, and the CMB. So the CMB is one of two pillars for the biggest story that we tell in science, which is the story of the whole universe. There's another piece of that puzzle that has to do with the reddening of light from different distant galaxies. We'll talk about all this eventually. And so that cosmological story that we're building up to, in some sense, is the big story of science, right? The Big Bang. And unfortunately, one of the two biggest pillars of that story is deeply threatened by this revelation, if it turns out to be accepted as the case. So, I don't think there's any reason that it has to be a nightmare. I think that it really just means there's a lot more work to do, and scientists love it when there's lots of work to do. I've never seen more happy scientists in my life. Like the biologists were so stoked during the pandemic that everybody wanted to talk to them for the first time in 100 years or whatever. And so I think there's a lot of money that can flow into research and into astronomy and astrophysics at that point. So it doesn't have to be a disaster, but it certainly will force us to reconsider things in a completely new way, all the way from stars to the entire story of the universe, I think. And that'll be really, really exciting and interesting. I don't know. I could see it happening at any moment. I could see it taking another 100 years. It's hard to say. We had the Ptolemaic system for the Earth being at the center of the solar system for almost, 1,500 years, something like that. So, could take a while. Who knows? Any final thoughts before we cruise on? All right, very good. I'm glad to see you guys are thinking about this stuff. It is a lot to wrestle with. But I think it's kind of exciting, too. And I also think, this is worth pointing out to you guys, too. This scientific method that we have, this idea that you can come up with natural explanations for reality, it's pretty young, ultimately. You might say, you could be generous and say it's 300 years old. But in all reality, professional science has only really been a thing in a career-driven sense with all this funding since after World War II. So we're basically babies at it. So I wouldn't expect us to have all the answers. In fact, I would expect we still have a lot to learn. And, it's very difficult to figure out how we can study reality, make definitive statements about it that people can put their faith in and trust in but they're also not final, and they're subject to being updated. That's a very fine tightrope to walk. I don't think anybody really knows how to make that easier. You don't want a science that's so flimsy that it can't be used to build upon, right? You don't want a science that's changing all the time. So there's something nice about the stability of it. But that also creates the problem that it's very difficult for us to change our minds as a scientific community. So it's tricky. Okay. All right. So the story that we're going to be building towards is we have this serious issue when it comes to grouping these stars together, because when we look up at the night sky, we see stars. We see really bright stars. We see really dim stars. And we want to be able to say something about those stars. We want to say how big they are, for instance. That would be really nice if we could say how big they are. If we can say how big they are, we could group them together. We could examine some information about their chemical content from the colors or the temperatures, and we could start to group them into families that we could start to tell a story about their lifetimes with. The big problem with that is the truck in the distance versus bicycle in the distance problem, right? So I think I mentioned this probably the first week or something, but if you're just walking down a street at night, you see a headlight coming towards you, and it's pretty bright. You don't really know whether it's an enormous truck, or whether it's a bicycle that just came around the corner and it's not that far away. They're both equal brightness, right? One's just further away, perhaps. The truck is just further away. The bicycle is closer. They look equally bright. This is the first problem we have to solve in astronomy, is how do we tell the difference between something that's close and dim versus something that's far away and bright. And it turns out to not be a very easy problem to solve. So that's what I'm going to kind of work towards in today's class. And hopefully, we have a few different possibilities for how we do that, although neither one of them is perfect. So the real answer we want is this question of luminosity. So the word we use for absolute power, so the amount of light that a star gives off, is luminosity. How bright it seems, we call that the magnitude of a star. And these are two very difficult to reconcile differences. And so we're going to start working towards that. First, though, let's talk about light a little bit. So we've talked about light as being some sort of interaction between atoms, right? And this is a really good way to think about it. Like, why does light fall off? Why does it get dimmer the further away you are? And it's like, well, one way to think about light is having this ray-like quality. So, you might think about it as two atoms that are connected. The shortest connection between two atoms is a straight line. So we can call that a light ray when this exchange of energy between these two atoms happens. However in the world that happens, we'll just leave the mediators out of it for now. It's interesting because you can kind of see here that if you are close to that atom in the first place, well, say it has 4 possible connections from it at some given radius when it's up close, right? As you move away, those get diluted, right? And they get diluted in this really predictable fashion, which is really proportional to the inverse square of how much distance is separated. It's the same principle for gravity, which is quite interesting. We don't have a ton of time to talk about gravity, but gravity is another kind of interaction that atoms have. It turns out to be a tensile interaction. Atoms pull on each other. Light actually has a little bit of a push to it, but it's the same process, the same inverse square relationship for that interaction happens with gravity. So basically, the further you are away from a source, the more you're diluting your ability to interact, simply based on surface area available for that interaction. And so this is going to play into the story with respect to luminosity versus magnitude. So this is magnitude, and it's a really preposterous scale, which I think is going to help us understand a little bit. I think this illustrates a bit of this principle where people build on old ideas that are not necessarily the best ideas. So there's this dude back in Hellenized Egypt. So Egypt got taken over by the Greeks at some point around turn of the millennium, let's say. the first the earliest, the zero, the year zero. So Hipparchus was this astronomer on the Isle of Rhodes, which is just outside Egypt, around 150 BC. And he prepared this really cool catalog that had thousands of stars in it. And he ranked them by their apparent brightness, which seems like a good place to start. And what he did is he basically said the larger the number that he assigned to it was, the fainter that object was. And he called this magnitude. So people used this system for 1,000 years afterwards, more than 1,000 years. So the brightest stars in his catalog were called first magnitude stars. And the weakest stars that he could see, this is before telescopes, by the way. The weakest stars he could see, he called sixth magnitude stars. Now, that worked out pretty good, but at some point, people, had telescopes so they could start to see things that were weaker than a sixth magnitude star. And they also started to really ask questions like, well, how much brighter is a first magnitude star than a sixth magnitude star? Like, is there a way to actually cluster these in a way that's discrete? It turns out there's a really painful mathematical relationship based on the fifth root of 100. But the basic answer is, a star that's magnitude 1 and a star that's magnitude 2 differ in brightness by a factor of about 2.5. And so each time that you move up in magnitude, you get dimmer by that same factor. So it's not a perfectly even scale. Now, if you look at the scale today, it's quite interesting because we've been able to see, this has the Hubble Space Telescope, which I assume was, when this figure was made, we didn't have the James Webb. James Webb's pushed this into even dimmer ranges because we can see more dim stars. We're closer to 30 now, not that much further than Hubble. But what's really interesting is that actually some of the brightest stars turn to be actually outside of the 0 point, right? So Sirius, which is the brightest star, is actually on the negative side. So that's really bizarre. So this magnitude scale is like, and of course things like the moon and the sun are absolutely negative because they're way, way brighter than any star in the sky. So it's an interesting system. And I'm not sure how Sirius didn't end up on Hipparchus' scale either, but it didn't, especially if we mathematically standardize it the way that it was in the 19th century with this 2.5 multiplier business. You basically end up with Sirius being down below 0. So an interesting situation where a system was developed when the technology, there literally weren't telescopes, and we tried to use that same system and cram all of the new observations into it, and we end up with a scale that's kind of bananas that goes from the negative all the way to the positive. So this is the kind of pattern that we see that people fall into oftentimes when we're trying to follow a tradition with respect to how we talk about something in the sky. And we'll see a couple more of those today where the classification system kind of fell off and didn't make sense and people just kept going with it, which makes, best case scenario, it just makes things a little more confusing. Worst case scenario, we can be led really far astray. So what else do we have? So we also can get the color of stars, right? So that's the other piece of the puzzle, which is going to help play into what we're talking about. We've been through this a little bit before, but the basic idea, just to refresh your memory, is that the more that a star kind of cools off, the peak of its black body temperature is going to shift slightly to the right. And so ideally, when we look at a star and we see its color, like it's very blue, let's say, we're thinking that it shifted to the left here, and there's a mathematical formula we can use to pull out what we think the temperature of that star would be. This would be really nice if it held up under scrutiny. Again, there's problems with this because if we have to start considering the lattice structure of stars as being different between them, then this temperature might not be the true temperature of the star. It might just be reflective of the particular material structure state of that star at any given point in time. So when Arthur asks, what would change? It's like, well, goodness gracious, a lot of things actually, because we wouldn't be able to make this really nice classification system like this, where we can say, oh great, the surface temperature of Spica is 28,000 and maybe 11,000 at its sunspot areas where it's cooler. It might not be that simple. It might actually reflect something more about the momentary structure of the actual atoms that are arranged on the surface of that star, which complicates things further. So I don't know. I mean, that's kind of exciting, right? There could be actually a lot of information that we could get out of it if we could find a way to cross-compare that. There's other ways to get temperature too, right? So the atmospheres of stars, you know, how hot is the atmosphere? Because different atmosphere temperatures are going to lead to different ions. Different chemicals are going to be able to exist in different energetic states in the atmosphere. So we'll see gas lines that might tell us something about the temperature of the star that we could cross-compare. And then we can compare it to what the black body temperature is and say, well, I don't think that black body temperature is right, therefore the lattice must be in a different state, and we might actually learn something really interesting about it. But for now, we're going to go with the idea that the color tells us the surface temperature. So that's one piece of information. We'll hang on to that. The next thing that we do is this stellar spectroscopy, which we talked about a little bit, which is really just, you know, pulling out the different lines from the surface. Now, this can be really useful because it turns out that those lines that we see in the surface, they're going to change depending on the motion of the star. And the motion of the star is going to be really useful in the method we're going to talk about today in terms of determining the mass of the star, because everything comes down to orbits, right? So if we have two stars that are orbiting each other, and the way that their lines are shifting tells us about the motion, then we can learn how fast they're orbiting each other, and we can back calculate how big they are. We'll go through that though, don't worry. So this is kind of interesting. Another case of a completely bananas classification system that emerged was the spectral class. So if you look here, this is the spectral system that we use today. The bluest stars are called O, the reddest stars are called M-class stars, and you know, everything in between them falls out. Why in the world did they come up with this O, B, A, F, G, K, M system? Anybody read this in the textbook? Remember this? So basically what they had tried to do is actually this young lady named Wilhelmina Fleming in the 1880s was looking at the hydrogen lines in the atmospheres of stars. And she basically decided that the ones with the biggest, strongest hydrogen lines would be called A-class stars. And that, you know, it went all the way down from that as the hydrogen lines got weaker, B, C, D, E, F, G. So originally it made some sense. They basically spectrally classed them according to the strength of their hydrogen lines. Later on, people decided that the temperature would be a better way of classifying them, but they stuck with the original stars that had been assigned to the first spectral system. And so you end up with this very bizarre system where actually we think of them in terms of temperature now, but they have kind of unrelated letters associated with them. So that's a bit unfortunate, but it's another system where you can see this incrementalism starts to build up these artifacts across time. So, you know, this happens though. Like, you guys know your keyboards, right? The arrangement of the keys on your keyboards. Like, anybody, you guys ever wonder why they're arranged that way? Okay, you guys know. All right, you had your hand up first. Yeah, go ahead.
Isn't it because if you typed too fast on a typewriter, it would like break?
Yeah, have you guys ever used a typewriter, anybody? They do. They actually jam up. They have these little hammers that come down and slam the ink on the paper across this ribbon. And if you type too fast on a typewriter, they actually like get locked up, right? So somebody had the genius idea that, hey, instead of having the keyboard have all the most used keys right next to each other, let's actually take the most used keys and space them out so that it makes typing harder, actually. Okay, good enough. It's like a hack for making these typewriting systems work so people weren't jamming their typewriters up. But what's really crazy is your guys' keyboards still have this QWERTY system on them, right? Which turns out to actually be the most inefficient way to set up a typewriter. You literally have the keyboard set up in the least efficient way possible. Why do we still do that? And maybe this answers like Kai's question a little bit from earlier. Why? We know that's not the best way to make a keyboard. Why in the world are we still doing it? Yeah.
We're used to it. You learn to type on that type of keyboard.
Because,
Traditionally,
yeah.
everyone's learned to
Why'd
type
you
on
learn?
that keyboard.
Why didn't your parents or your teachers teach you a better way to type, right?
Well, back in like the 40s and 50s, typing was actually a class that women primarily would take.
That's
You
true.
learned to type on a typewriter.
That is
So
true.
the typing class just kept getting moved along, which is the reason why we, kept the keyboard being. I'm sure we've all been trying to fill in our password on Netflix on the TV. If you go too far, and you're like, oh, why is it so hard?
Yeah, it's absolutely amazing if you think about it, that, nobody in the age of digital typing, which we all grew up under, right? I never used a typewriter in school. I think my parents did, perhaps. But none of you guys used typewriters in school. It's amazing that nobody actually started teaching the next generation of kids to use a typewriter that would allow them to type really fast, right? And of course, there's been hacks over the years, right? Like quick swipe, texting, and things like this. There's ways around it. There's actually a whole weird community on the internet. Maybe you guys are aware of it. Stumbled into it, of people who have alternate typewriter or type keyboards, right? This is like a whole thing. You can actually teach your computer to learn any set of. You can put little films across your keyboard, and you can retrain your computer to type. And some people do that, and they can type at incredibly fast speeds. But the point that I'm trying to make is that we're creatures of habit, and we learn things from one generation to the next, and science is exactly the same way. That's why science tends to snap catastrophically in these things we call paradigm shifts or scientific revolutions, because people are really creatures of habit. We all are. Even the smartest of us are creatures of habit. We learn things from the previous generation, and we just do them because that's what we're supposed to do. So, I don't know. It's fascinating. It doesn't just happen in science. There's something deeply human about the way this is done. So, yeah, I just want to give you guys a quick little picture. So that's our star down there. Nice G-class yellow dwarf. That's our sun. They get much, 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 much bigger. And it turns out they're mostly much, 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 much smaller. So we'll talk a little bit about some of these spectral classes. The spectral classes go all the way down. Recently, they added a couple more classes, these LYTs. They added these essentially to account for brown dwarfs, because people started to very recently start thinking about brown dwarfs as essentially being stars. I think they referred to them as failed stars for the most part, almost stars. I see no reason why they can't also used to be stars as well. That's another piece of the puzzle. But we've added a few more spectral classes to deal with the really cold ones. I did want to say something though about we'll get to it, I guess, in a minute. Okay, so presumably this goes all the way down. Jupiter is at 125 Kelvin. It's very cold. What's interesting, if you go past Jupiter, right, you're going to end up into really cold stuff, right? Like planets, essentially, which are really cold compared to stars. But they can be fit onto the same spectral class if you really want to, because planets do seem to be in different stages of cooling themselves. And so you start to really blur the line between stars and planets at some points, especially when it comes down to how in the world you make some of these planets, which is beyond the scope of this class. Okay, so let's get back to trying to figure out how big these stars are beyond just their color. So, from the color, we have some suspicion that the more atoms you have in one place, the hotter it's going to be. That seems to play out for stars that we can see. For planets, Jupiters, and so forth, they're smaller. Brown dwarfs that are Jupiter-sized but have more mass to them, they're going to be hotter. So there seems to be some relationship between hotness and size. Might be complicated if we're misinterpreting the black body curves, but there's some trend available there. But it's not enough. It's not quite that simple for us. So we need to still keep trying to figure out how we're going to tell the size of these things. So one way we can do this is by looking at the broadening of lines. So we talked about this before, that these individual lines in the atmospheres of stars, they can tell us a bit about the composition, but they can also tell us a bit about the mass of the star itself. Because as there's more gravity, the bigger the star is, the more spread out those individual gas lines will be. And there's a limit to it. It occupies maybe a few tens of frequencies. It's not anything like a rainbow, but you see the broadening of these peaks. And so we can get a little bit of information by how broadened those atmospheric peaks are. The other thing we can get from those lines is something about the motion of these stars. So you guys heard of this Doppler shift idea before? You guys have probably experienced this with sound, right? So you ever notice how when like a police car or an ambulance goes by, you can kind of hear the pitch increasing as it comes up towards you, and then it gets louder. It's like woo, as it goes away, the pitch goes down, right? And pitch is kind of like color in the light realm. And the basic idea is this, that as you, let's say, this motion being relative, but as this observer over here is seeing this light source come towards them, they're going to experience more of those peaks and troughs of the light waves than they would otherwise if it was stationary. And their experience of having more of those peaks in a shorter amount of time is going to give them the illusion that it is a shorter wavelength. In other words, that it's a higher frequency, there's more waves per unit time, and they're going to perceive it as being slightly bluer. And the opposite will happen if a source is moving away. So it's kind of the same thing as an ambulance, but you got to think that low pitch for light is kind of like reddening, and high pitch in the sound realm, the analog for light is the bluing of the light. So this is cool because if this is all things being equal, we look at the atmosphere of a star and we're like, okay, there's a peak over here that's roughly corresponding, this has all been assigned in laboratories very easily. You essentially take a Bunsen burner and you can burn different elements and see what color the gases or the individual elements burn at. They give off these individual colors. And so you can say, okay, there's a peak at, 400 nanometers or something that corresponds to this hydrogen emission line. If that's moving, then we have some idea that that star is moving as well. It's coming towards us, let's say. Or if it's changing across time and it's moving backwards, then we get the idea that the star is kind of oscillating, perhaps. And this turns out to be really useful. So here's an example of that. You can see a particular line. It doesn't matter what element it is, but let's say it's a hydrogen line of some sort. It's being red shifted in the upper category here, and it's being blue shifted down below. And what's interesting is that all the lines, right, doesn't matter what element you're looking at, they should all kind of be shifting together, right? You shouldn't just have one atom in the star that's moving towards you or moving away from you. They should all kind of be moving together. So you can use this to calculate the speed at which that star is moving either towards you or away from you. This is actually the exact same principle that those annoying cops with their radar guns on the highway use to pull you over. Has this ever happened to anybody before? Yeah, of course. I used to have motorcycles, and they're basically impossible to drive at the speed limit. And yeah, this was always happening to me. So saved a lot of money by getting rid of them. And this is essentially what the cops do. They shine a light off of you. They wait for the reflection of that light to come off of you. Now, it's in a wavelength that's not visible, right? You don't see a big flashlight. But they're basically shining these radio waves off of you. They're bouncing off of you. They're coming back. And depending on how fast you're moving, the reflection essentially reports that to them. And they see this analog, this sort of red shifting or blue shifting. So it's a very similar process that we use in order to see the star's motion as well. So this is the Doppler effect. Now, this can tell us a couple of different things. So one thing it can tell us is the actual rotation of a star. So this is kind of interesting. So, as something rotates, one side of it, as it's rotating towards you, that light, let's say, that's being emitted, that part of the star is going to be coming towards you. The other part of the star that's rotating away, the light is actually going to be receding from you. The result is that the overall spectrum is going to be smeared out a little bit. So the lines are going to be both red shifted and blue shifted together. So you see kind of a departure of the individual lines. So you can get some information about the rotation. This is tricky because there's obviously other reasons, like the one we just talked about with pressure broadening of lines as well. How do you tell whether it's due to pressure or whether it's due to the rotation of the star? I don't know. It's actually very difficult. You maybe made yourself more problems than solutions in that case. The idea is that if we trust the black body temperatures of the stars, then we know the blue ones are the big ones, and so on and so forth. If that's not that simple, then we have a real pickle when it comes to interpreting the rotational motion of stars. Okay. I'm going to skip this a little bit. Let's talk a little bit about what our local population of stars looks like, just in terms of color and class, the different spectral classes. This is a picture of our own local neighborhood. It's obviously a model with the sun. Nobody's gone out and taken a picture of this, but they've reconstructed this diagram. What's really interesting is that most of the stars around us are really dim. About 75% of them are the red M-class dwarf stars, the ones that are the furthest one down on the spectral class that we look like, all the way from O to M, right? So most of the stars around us are way tinier and way dimmer than us. And this is really interesting. I think that this is an interesting meta phenomenon that happens in sciences. We tend to see what's most obvious near us. So if we think about the 20 brightest stars, you go out in the night sky and you look at the 20 brightest stars, you might be tempted to say, well, those are probably the ones that are closest to us. It turns out because those stars are something, for the most part, on the order of 1,000 light years away from us. The closest star is actually only 4 light years away from us, but it's very, very dim, and so we wouldn't see it necessarily. So again, it's very, very difficult. This is maybe a good figure for you guys to get a sense of actual layout of the way that our local neighborhood in the galaxy looks like. So, our star somewhere down here in this 50 stars versus 200 stars in the bucket, if we just sort these by how many types of each type of star, we would see one star that's super blue, and we would see 200 stars that are red or almost red, orange, right? So most of the stars are really, really dim. And that's really quite interesting because actually if you extend this, right? If you extend this down, you would imagine that there would probably be lots of stars that were so dim we couldn't even see them actually. And maybe those are stars in the brown dwarf region. It's actually very hard for us to estimate how many brown dwarfs there are. Why? Because we can't see them. They're cold. So things are not necessarily how they look, and that's quite important as we move forward here. One hope that we do have in terms of gauging the distance is binary stars. So I don't know if you guys realize this, but most stars actually occur in pairs. Actually, the number goes up, the proportion goes up every year. So I think at this point it's somewhere in the neighborhood of 85% of the stars that we can see with our telescopes have partners. So not only do planets orbit the stars, but the stars orbit each other. Our solar system's kind of weird. We haven't found any partner star for ourselves. And it brings up all sorts of interesting questions, like, did we used to have one at some point in time? If we don't have one, is that important for why our solar system looks so weird? Maybe. But binaries turn out to be really interesting pieces of the puzzle because you actually have a system where you can observe the motion of a star with respect to another one and start to also make some interesting comparisons between their masses. And these turn out to be the keys for how we can gauge the masses of stars. So but binary stars are really interesting. We're going to talk more about these in the future. In general, there's usually a little one and a big one. And there's a really fantastical story that we're going to tell about these because the little ones tend to be often very bright white and blue. We call them white dwarfs. And they take a real star role in the story of the evolution of stars, especially in this explosive supernova process we're going to get to. Oftentimes, it's very difficult to even see one of the partners. The only thing we know is that a star appears to be orbiting nothing, essentially. And so we have to assume that there's something very heavy there that it's orbiting that we can't really see. And sometimes we can see them, and we call them white dwarfs. Sometimes we can't see what's there, and we call it a black hole, actually, which is quite interesting. Now, we'll get into the story of black holes and white dwarfs later, but needless to say, they're a big piece of the binary puzzle that we're going to be drilling into here in a second. So these visual binaries are something that we're going to mess with. Those are ones you can actually see. Yes. Just a preview, because we're going to be talking about that. The thought is that these white dwarfs are this incredible form of matter that we've never seen on Earth, which is unimaginably compact and has so much gravity that it's stripping off the material from its partner star, right? Exactly, yeah. So again, what do we actually see? We see a star that's orbiting something that's too little to make sense. It's very dim. That's a good way of putting it. Now, I've kind of been previewing this paradigm that people have, which is that things that are really bright should be really massive. If they're really big, then they can do a lot of fusion and they can give off a lot of light, right? So if something's really dim, it either must be really far away or it must be really small. But this is perplexing because, as we'll see, we're able to figure out that some of these aren't that far away and they're still really dim and they're huge. So how do you have something that's really dim and huge? That's a huge problem, right? Especially for a gaseous star. That's the only way to solve that is to propose that there's exotic forms of matter that we've never seen on Earth before that are super heavy, and the star is really, really tiny. So the explanation that's given is that those dwarfs, those white dwarfs, they are the size of Earth in radius, but they have the mass of many, many stars crammed into their tiny little space, right? Now, I brought this up. We'll come back to it, but I brought this up to you guys before that you can really change the optical properties of a material by literally just changing the structure in which the atoms sit. Diamonds and carbon soot are a really great example, right? One is very optically transparent. In other words, it's quite dim, and the other one is completely opaque, so it would be glowing quite a bit. And that's not because there's any difference in the size of those bodies necessarily. It's just because you have a different arrangement of the atoms on their surface. This is a problem that the gaseous sun doesn't have to deal with because there's no such thing as a lattice in a gas, so it doesn't matter. So the whole story of white dwarfs and black holes is under assault, but we'll get to it down the road. We're getting a little ahead of ourselves. All right, so let's take these binary stars at face value. So binary stars are really nice because what they're going to allow us to do is to use the motion of these lines, this Doppler effect that we just discussed, and calculate the motion of one star around another. Why does that matter? If we have the motion of the star, I'll show you in a second, we can essentially back calculate how big it is because your gravity is essentially proportional to how fast things zip around you. So this is called spectroscopic binary analysis. And it's all built on this simple Kepler's laws, which I'm not going to bore you with too much. You might have a question in your workshop about this. We did it in depth last semester. But the basic idea was proposed a few hundred years ago by Kepler, who made this realization. And this is around the time that the whole story of the organization of the solar system was starting to fall apart, and Kepler contributed to that. Copernicus built on it, Galileo built on it. But Kepler was one of the first people who really took the star catalogs and tried to come up with a model that would work where the sun was at the center of the solar system. He did that by moving away from the perfect circle and moving on to this thing called an ellipse, which is basically just a stretched out circle. And he realized that if he put the star a little bit off center on the ellipse at one of its focal points, that he could explain the motion of the bodies in the solar system. So the central idea, which he deduced, was that the period of the motion of those stars, so how fast they go around, is proportional to the size of their orbit. So when something is really far away, it slows down. When something's really close, it speeds up. And actually, Newton came along later and decided that what decided the nuances of this relationship was this concept called mass. So how much stuff was there? In other words, things that were bigger were going to zip around faster than things that were smaller. Distance also matters, right? Why does this matter to you guys? This matters because if we know the distance of the orbit of these binary stars, and we know how fast they move around each other, the period of their orbit, then the last variable that falls out is the mass of those stars, the combined mass of those two stars. So the way we do this is we look at the lines. So we have essentially two tracks, one for each one of the stars in the system. And the basic idea is that if we know the average velocity from the way that these Doppler shifts happen with the lines, that we can essentially time how long one star moves in one direction versus the other. So we count it, we watch that line shifting for a number of days, and we say, okay, it took 3 days. We know the speed from the Doppler shift, right? We can calculate that just like the cop using his radar device calculates the speed that you're going. We calculate that. And then all we have to do to get the distance of separation is multiply that speed by the amount of time that it takes for it to go and reverse in direction. So then we get the distance, essentially. So measure the speeds from the Doppler effect, determine the period, so how long the stars take to go through that orbital cycle, in which the direction of those lines reverse. And then we go back to that Newton-Kepler relationship, plug in our distance, plug in our separation, and the masses of the combined masses fall out of it. So we have a difficult time separating out those two masses, which means we know the total mass of the stars in that system. Usually, the more massive something is, the closer it's going to be to the center. So I mentioned to you guys that Jupiter and the sun essentially orbit a point that's slightly outside of the sun, right? So the one that's moving the least is the one that we deem to be the more massive of the two. This is where things get really complicated with the white dwarfs, because oftentimes the thing that's the dimmest is the one that's moving the least, which leads us to believe that that's the heavy one. So this gets us a little bit closer, because all of a sudden we can look out and see binary stars. Most stars are binary, so we can do this with most stars. We can look out and do this spectroscopic binary analysis, where we can say exactly how big something is. If we know how big something is, then the good news is we know whether it's a truck or a bicycle all of a sudden, right? When it's coming down that country road. We see how bright it is, we know how big it is, and now we can say the relationship between how bright it appears and how bright it actually is. And that gets us essentially the last step towards saying what the true luminosity of that star is and what the true mass of that star is. Now, this, of course, gets complicated depending on how much we can trust the idea that the brightness is exactly a result of its mass in the first place. But I'm going to keep coming back to that because it's a very difficult concept to wrap your head around, and it's obviously not something that the textbook is going to worry about too much. So let me ask you this. What kind of questions pop into your head at this moment about this process of determining the mass, the size, the luminosity, why it matters? Yes.
Does it matter when we're like, this is just mostly a question, does it matter when we're trying to figure out like the makeup of the stuff?
So we can know the makeup just based on the composition, but yeah, it does very much matter. So we can see the elements that are in its atmosphere. But yeah, absolutely. Determining the size of the star is everything when it comes to grouping them together. And this is, I don't have time to get into grouping the families together right now, but the next thing we're going to do is we're going to start grouping them by temperature and luminosity. Luminosity being a very optimistic readout of mass, because there's a very hopeful direct relationship between how bright it is and how big it is, which I keep hinting at might be extraordinarily complicated in the future. But for the moment, if we know the actual power output of the light, so we've dealt with this truck versus bicycle problem, then we can rank them on a graph where you essentially say the most luminous stars versus the temperature. And we can start to put together a story of how big stars evolve across time and cool or don't cool or explode or expand or all of these things. Those trends will start falling out. I couldn't finish this entire story of how we group these things together, so I think you guys are going to just have to hang on, and we will assemble the family diagram next time, and I think all of these ideas will pop into place then. So enjoy the rest of your week, and we will continue with it Thursday.